Hi there, welcome back to my channel. In this video, we will take a look at the last example that we left, and we will look at an example of a 3x3 system. Our system was given by x dot equals alpha x minus beta y, and y dot equals beta x plus alpha y. Now, whenever you are given a system, the first thing you need to do is to write its matrix form. We represent our matrix by C, alpha minus beta, beta, alpha. Note, the eigenvalue for this is simply alpha plus or minus I beta. Now, the eigenvalues are made up of the complex and complex conjugates. To prove this, we will use the determinant and trace approach to verify our solution. So we have tau to be equal to the sum of the elements on the diagonal, alpha plus alpha, giving us 2 alpha. And for the determinant, we'll have alpha times alpha minus beta times minus beta. And this will give us alpha squared plus beta squared. Furthermore, to find our eigenvalues, we use this expression. Substituting our value for tau and delta, we have 2 alpha plus or minus the square root of 2 alpha all squared minus 4 times the value of delta. So we have alpha squared plus beta squared all divided by 2. So lambda will be equal to alpha plus or minus the square root of 4 alpha squared minus 4 alpha squared minus 4 beta squared. This all divided by 2. Then we have alpha plus or minus the square root of minus 4 beta squared divided by 2. Now we can write this as alpha plus or minus. We have the square root of minus 1 multiplied by the square root of 4 multiplied by the square root of beta squared, all divided by 2. Next, we can write this as alpha plus or minus the square root of minus 1 multiplied by 2 multiplied by beta, all divided by 2. Now, the square root of minus 1 is given by I, which is the imaginary number. So we have lambda to be equal to alpha plus or minus I. These two will take care of these two, beta. We have verified our eigenvalues. Whenever you are given a dynamical system where you have your matrix to be in this form, then you can go ahead and write down your eigenvalues. Now, the process of finding the eigenvectors is the same as the previous ones. So what we will do now is rather to find your E of t. Now, E of t is given by the exponential of the diagonal of all the lambda times t. Now, this is E of t. If you are asked to find the exponential of your matrix, it is always without t. Okay, so this is the exponential of a matrix. Whenever you're asked to find the exponential of a matrix, you find it without t. Now, what we are actually going to find is E of the diagonal of the lambda, which is given by E raised to the power lambda. And we said our lambda is given by alpha plus or minus I beta. Now, since alpha and beta are commutative, it implies we can write our E raised to the power alpha plus or minus I beta to be equal to E raised to the power alpha times E raised to the power plus or minus I beta. Now we recall that when you have E raised to the power I times a certain value, let's say theta, we write it as the cos of theta plus I sine of theta. Now, if we have E raised to the power minus I theta, you're going to have the cos of theta minus I the sine of theta. So if you want to combine them, E raised to the power plus or minus I theta, you're going to have the cos of theta plus or minus I sine of theta. In this case, we have E raised to the power plus or minus I beta. So this means you're going to have the cos of beta plus or minus I the sine of beta. We have the real part of E to the power I beta, and this will be the imaginary part of E to the power I beta. For our given solution, we will have E to the power lambda to be equal to E to the power A multiplied by the real part of E I beta minus the imaginary part of E to the power I beta. Then we have the imaginary part of E to the power I beta, the real part of E to the power I beta. So since we have this, we are going to substitute the values we have for each one of them. So E to the power lambda is given by E to the power A multiplied by, we have the cos of beta, we have minus the sine of beta, and we have the sine of beta, and again we have the cos of beta. And this is going to be the form of our solution. So for the exponential of a matrix, this is what we're going to have. Now, if you want to substitute this value into the solution, x of t, you're going to have e raised to the power c t x naught. And this expression is given by p e of t p inverse times x naught. So we are still going to use the same process of finding the exact solution for our system. And there's a special way to solve your p and p inverse. We will go about that when we take a look at an example. 3a, we had alpha to be equal to 3 and beta to be equal to 2. If we let our matrix C to be equal to 3 minus 2, 2 and 3, it means our eigenvalues are going to be 3 plus or minus 2i. These are our eigenvalues. Our eigenvalues are composed of the complex and conjugate. So the complex and complex conjugate are our eigenvalues. We also write the behavior of the system. So the system is an unstable focus at the origin. As we've discussed previously, when the real part of the eigenvalue is negative, the system is stable. And when the real part of the system is positive, it is unstable. So since we have 3, which is positive, we have an unstable focus. Next, we are going to find our eigenvectors. We're going to use the positive part of the eigenvalues to solve it. So we are going to use lambda equals 3 plus 2i. The expression for finding our eigenvalues is a minus lambda I times our eigenvector equals 0. So we have a minus our lambda is 3 plus 2i times I times v equals 0. So next we have 3 minus 3 minus 2i, and we have minus 2. We have 2, and we have 3 minus 3 minus 2i multiplied by your x and y equals to 0, 0. Now this gives us minus 2i minus 2, 2 minus 2i, x and y, 0, 0. Again, we use the first line, so we have minus 2ix minus 2y equals 0. We divide both sides by minus 2. We have ix plus y equals 0. Now we have ix equals minus y. And when we divide y by x, we're going to have minus I over 1. So our eigenvector is given by x and y, which is equal to 1 and minus I. Now we can't mix our real and imaginary numbers together. We have to separate them. So doing so would give us 2 eigenvectors simultaneously. So this will be equal to, you have 0 minus I for the imaginary part plus 1, 0, which is finally written as I 0 minus 1 plus 1, 0. Now remember, we are only taking these values without the I. You know that this is for the imaginary part and this belongs to the real part. We have to keep that in mind. We go ahead and write our P matrix. We write the imaginary part first, followed by the real part. So if this is U and this is V, we write U first and then V. So our P is equal to, the value of our U is 0 minus 1, and the value of our V is 1, 0. Now, if you want to find P inverse, it's 1 over the determinant of P multiplied by the adjoint of P. So we have 0, 0, 1, minus 1. And for the determinant of P, it's plus 1. So our P inverse is given by 0, minus 1, 1, 0. Next, on diagonal of lambda. The diagonal of lambda is given by the eigenvalues. And the eigenvalues we had in this expression was 3, minus 2, 2, 3, which is the same as our matrix. So since we have the same value of our matrix as our diagonal, it won't change. Now, to write the exponential of this matrix, you're going to have e raised to the power 3 and the cos of 2 minus the sine of 2, the sine of 2, and the cos of 2. I'm not adding any t to the diagonal, so I can't add any t to the cos and sine. This is the exponential of the matrix. So to write our e of t is given by e, the diagonal of lambda t. So now we can add it. We have e to the power 3t multiplied by the cos of 2t minus the sine of 2t, the sine of 2t, and the cos of 2t. So to write our solution, x of t is given by e to the power c t x naught p e of t p inverse x naught. So substituting our values, we're going to have our p, which was 0, minus 1, 1, 0. Our e of t, which we have over here, we have e to the power 3t plus 2t minus e to the power 3t sine of 2t, e to the power 3t sine of 2t. This is supposed to be together. So we have 2t and then e to the power 3t, the cos of 2t. So we add our p inverse 0, minus 1, 1, 0. Then we add our x naught. So this is going to be the solution for our system. In the next example, we are going to focus on a 3x3 system and other 3x3 systems. So see you in the next video.